So here's our second example for our rotational kinematics. We have a child's top is spun with angular acceleration alpha is equal to 5t cubed minus 4t with t in seconds and alpha in radians per second squared. At t equals 0, the top has angular velocity of 5 radians per second and a reference line on it is at angular position of theta equals 2 radians. That information that they give you there, it's helping you find those C terms when we take an integral. Because for letter A, it says obtain an expression for the angular velocity of the top. So just like linear motion, when we go from acceleration to velocity, we want to take the integral. Of course, here we have an indefinite integral, so we are going to add that C term like we talked about in class, but here they give us information in order to find C. So for letter A, when we are finding the angular velocity with respect to time, remember first we add 1 to the exponent, and then we're going to divide this whole thing by that exponent. So we get 5/4 times t to the 4th power, which ends up being, if we divide 5 by 4, we end up getting 1.25, so 1.25 t to the 4th, and then minus, and then this, of course, is just like a imaginary 1 exponent. We're going to add 1 to that, so we get 2. We divide 4 by 2, so that ends up being 2 times t squared. And then, of course, we add that c term, which was very wiggly. We're adding c. So in order to find what that c is, we know that here they tell us at time t equals 0, the top has an angular velocity of 5 radians per second. So that means that our angular velocity is 5 radians per second at a time t equals 0. So that this term is 0, this term is 0, and then c ends up being 5 radians per second. So here, in order to get our complete function of angular velocity with respect to time, we get 1.25 t to the 4th minus 2 times t squared plus 5 radians per second. So there's our function there for letter A. Now for letter B, we want to obtain an expression for the angular position of the top. So remember, when we're going now from velocity to position, again, we're just taking the integral. So same thing here. We take that exponent of the first term, 4, we add 1, we then divide 1.25 by that 4 plus 1, which is 5. So theta of t, 1.25 divided by 5 is 0.25, t to the 5th, minus, and then of course we're adding 1 to that exponent 2 now, so that becomes 3. We divide 2 by 3, which is 2/3, or 0.67, t to the 3rd, and then plus 5t for that last term. And then of course we're adding c again, and then in order to find what c is there, it says at time t equals 0, the reference line is at angular position 2 radians. So that means this is going to be 2 radians. And then all of these 0 minus 0, because t is 0 here. So that means c is 2 radians. And so we end up getting our function of position with respect to time is 0.25 t to the 5th minus 0.67 t to the 3rd plus 5t plus 2. And that's our answer for letter B.